So whenever we talk about modulation, we can consider the extent to which a signal has been modulated, and that extent can be captured in the modulation index. So we can calculate a number in relation to the amount of modulation which has been applied to a signal. Okay, so the modulation index, it's often necessary to define the level of modulation that is applied. So we want to know how modulated signal is, so we can appreciate if there's under or over modulation in order to maximise the efficiency of the communication within the constraints of the physical channel. So in order to have a standard method of achieving this, we use a factor known as the modulation index. And in parallel with the modulation index, we can also represent this as a modulation depth. So the modulation depth is really just a percentage representation of the modulation index. So for an undistorted amplitude modulation to occur, the modulating signal voltage must be less than the carrier voltage. Okay, so the modulating signal voltage must be less than the carrier voltage so that it can be supported within that carrier wave. So the modulation index should therefore be a number which is between 0 and 1. So it represents the modulation on a scale between 0 and 1 in terms of the modulation in relation to the carrier wave. If the amplitude of the modulating voltage is higher than the carrier voltage, M will be greater than 1. And when we have an M which is greater than 1, this represents a distortion of the modulated waveform. So we've got a modulated signal, but it will be distorted and won't accurately convey the information which we wish to send. So the relationship, therefore, between the amplitude of the modulating signal and the amplitude of the carrier signal is important to be aware of. Okay, so we have a modulating signal and we have our carrier wave, and then we have our modulated signal which is being carried by our carrier wave. So we want to understand the extent to which the original signal is modulated on the carrier wave. So as an indicator of the level of modulation on an amplitude modulated signal, the modulation index is important to know. If it's too low, then it doesn't utilise the carrier efficiently. If it's too high, then the carrier can become overmodulated, and this can cause distortion to occur, so interference in the signal which is being communicated. So modulation indices are described for various forms of modulation. The amplitude modulation index can be defined as a measure of the extent of amplitude variation about an unmodulated carrier. Okay, so this describes the extent to which the modulated carrier varies around its static unmodulated level. Okay, so how modulated is the signal in order to convey the information being communicated? So the modulation index, how do we calculate this modulation index? We have the modulation amplitude M and we have the carrier amplitude A. And these values are the peak values for both the carrier amplitude and the modulated amplitude as well. So multiplying this modulation index by 100 gives the percentage of the modulation. So if we have a carrier voltage of 9 volts and the modulating signal voltage is 7.5 volts, then we have a modulation factor of 0.83 and the percentage of this modulation, so the modulation depth, is 83.3. So there's some further examples again at the end of these series of slides. Okay, so this complementary figure to the modulation index is known as the modulation depth, and this is the modulation index expressed as a percentage. So a modulation index, therefore, of 0.5 would be expressed as a modulation depth of 50%. So what does this actually mean? So this means that the carrier amplitude varies by 50% above and below its unmodulated level. So when we have our carrier wave, And once we modulate the information on top of the carrier wave, then the wave then has an amplitude which varies by 50% above and below its unmodulated level. When the modulation index reaches 1, so we have a depth of 100%, then the carrier falls to 0 and rises to twice its non-modulated level. Okay, so it falls to 0 and rises to twice its non-modulated level. Okay, so we're reaching here the outer limits of the carrier wave in terms of its ability to be modulated any further. Any increase of the modulation index above 1, okay, above 100% depth, causes overmodulation to occur. So any increase of the modulation index above 1 causes overmodulation. Okay, so the carrier level would try to go below the 0 point. So it would try to go into levels which the carrier wave doesn't support. And this has the effect of giving additional sidebands from the phase reversal, so that phase modulation, that extend outwards, and they can extend outwards to infinity. And this can cause interference in the signal which is being communicated if it's not removed. So that's a situation which we want to avoid. Okay, so to calculate the modulation index, and this is a calculation which you should be familiar with for your exam and also for your tutorial on Wednesday night. Okay, so we have a modulation index which is calculated from the maximum voltage and the minimum voltage of our signal. So the modulation index is calculated using this equation. Okay, so if we have a signal with a maximum voltage of 10 and a minimum voltage of 3, what is the modulation depth? So we use this to work out the modulation index, and then we convert that to the percentage. So we have a modulation index of 0.538, and we convert that to the percentage, and we get 53.8% modulation depth.